Good day and welcome to the Refrigeration Masterclass webinar series. I'm Michael Bellstedt from Minus 40. I've been in the refrigeration industry for around 30 years and I'll be sharing my knowledge and experience with you today. So first we do part one, which is understanding refrigeration basics. Now before I do that, interesting in the Australian context is the beginning of refrigeration. And very few people know that a gentleman by the name of James Harrison was actually the inventor of vapor compression refrigeration as we know it. And he's from Geelong, or he was from Geelong, pretty close to where we are right now. And he built that in 1851. It was a system that used ether as a refrigerant, which we don't use today. And it was used to make ice. And the ice, I learned recently, was used in the morgue in Geelong. And yes, the Americans tend to dispute this a lot, and they claim to have built the first system. But if you do the research as I did, we found that that was actually in 1852. So we did beat the Americans to the refrigeration game. So there is a historical connection, and we celebrate James Harrison in the industry. We have an annual competition for young tradespeople. It's called, and the guy who wins that, or the girl, wins the James Harrison Award. So there you go. Now, refrigeration in its simplest sense has four components. And I need to explain these because all about how systems use energy depends on basic understanding of refrigeration. So this little diagram here already shows that. We have a compressor, a condenser, expansion valve, and an evaporator. Every refrigeration or air conditioning system will have those four components. So we'll start with the compressor. Now remember, it's a vapor compression system. That's the fundamental principle here. So a vapor compression system takes vapor, which I'll explain to you where that comes from. It compresses that to a gas, which is hot and at a high pressure, still a gas. From there, it goes into a condenser, which typically is the outdoor unit with the fans on it, where the gas is first cooled and then it condenses, which is what the name suggests. So it becomes a liquid. Liquid comes out of that unit. Liquid travels to this important device called the expansion valve. What that does is pretty much what happens when you open a bottle of Coke. That release of pressure causes some of it to evaporate. It immediately cools down. It's still a liquid. That liquid then travels into the evaporator where it absorbs the heat, evaporates, because if something evaporates it has to absorb heat. It turns into a vapor, makes that thing cold, and there's air traveling over that, so that's where the cooling is being done. And that vapor then finds its way to the compressor and the cycle repeats itself. So all of these things, except the expansion valve, use energy, but all four of them need to be running the right way to minimize the energy use. And that's what we'll be talking about today. So if you look at that in a different pictorial representation, you've got a compressor, which is the little diagrammatic thing at the top, a condenser, which typically looks like what you see there on the slide on the right hand side. That's the air-cooled condenser. Expansion valve, which is a little valvey thing which most people won't see because it's hidden, and then the evaporator, which is the unit inside the cool room. And if expansion valve and the evaporator are the cold bits of the refrigeration system, and the compressor and the condenser are the warm bits. So they need to be outside, of course, because you don't want them inside your cool room. And the correct location of those is one thing we'll talk about later. So where is refrigeration energy used, or where is refrigeration used in an energy system, and refrigeration system? Now, most of the energy is used by the compressor, which is kind of logical because it does all the hard work of compressing the vapor. But by no means is that the only energy that is being used. We have the condenser fans, which I showed you before, and the evaporator fans, and they use a lot of energy because they tend to run all the time. And it always surprises people to realize how much energy is actually being used, for example, by the evaporator fans. And it's often very easy to save energy with the fans and more difficult to save it with the compressor. So you go for the low-hanging fruit. So that's why fans are quite important in the discussion. And then we have the defrost heaters, and this is where it's kind of sad because we spend a lot of money in terms of energy to generate refrigeration, and about 20% of that is just used to make ice. Right? It doesn't do us any good. It just makes ice in your fridge, or it makes ice in your cool room. And then we have to spend more money on more power to defrost that. This doesn't happen in your home fridge, it just defrosts by itself. But in a supermarket or something, there's actually electric heaters in there which melt the ice back down again. So you pay for the ice twice, when you make it and when you melt it. So we can do things to minimize that defrost energy as well. Now, when it comes to refrigeration, there are two main areas: commercial refrigeration and industrial refrigeration. Like a dichotomous industry we have. The commercial refrigeration uses the air-cooled systems you see on the left of the slide, uses the freon refrigerants or the synthetic refrigerants, which I'll talk about a lot in the next few slides, and it uses copper, because copper is compatible with freons. And copper is relatively cheap and easy to install. You just have to solder it. Ammonia is generally used for the big side of the industry. Ammonia doesn't like copper, so you have to use steel. So you need a different set of tradespeople to do ammonia install. So generally, that's why it's a dichotomous industry. You have the industrial installers using big industrial systems, using their bunch of trade people, and then you have the commercial industry. Much of what we'll be talking about today is commercial, because that's where most of us encounter refrigeration. So commercial refrigeration on the left side of the table is usually the smaller systems, stuff that you encounter. So cool rooms, small freezer rooms, supermarkets, air conditioning, that's all done with commercial refrigeration technology. And it's normally close to the public, because up to now, and I emphasize up to now, these refrigerants have been safe. They haven't been toxic and they are not flammable. That's about to change. And it's the gases that we currently use, and a couple of them are listed there, are multiple. And you see, besides all those funny numbers, 404A, 134A, 410A, 407C, 407F, 448A, and I can carry on, that's only about 10% of the refrigerants out there. There are two other gases coming in. Carbon dioxide, believe it or not, is becoming a very important refrigerant. And hydrocarbons, barbecue gas, is actually quite a good refrigerant. And then on the industrial side, it's mainly ammonia, but increasingly also carbon dioxide. So we're actually going through this interesting evolution in our industry, is that one common refrigerant is being used on both sides, and this dichotomous refrigeration industry might come together. But that's just a little aside. So ammonia, you'll find that in the big cold stores. You'll find it out in the Laverton areas and in Melbourne, where we have the big cold stores or the big meat works, and that's where it's used. It's very, very efficient, and that's the reason why it's being used. But normally not where there's public access, because ammonia is highly toxic. So you would not use ammonia in your domestic fridge, and you would not use ammonia in a supermarket. Okay, so that's the commercial and industrial. So 95% of the walk-in cool rooms, which is the topic of this refrigeration masterclass, use commercial refrigeration. Taking another step back, our industry has been around since 1850, as I emphasised before, and it's gone through a number of evolutions. But it started off with a whole lot of refrigerants that were using substances that were available at the time, what we call natural refrigerants. So ammonia, carbon dioxide, ether, these gases were used initially. And then a little bit later, they started developing other things like sulfur dioxide and methyl chloride, which were very toxic and very aggressive. So if you speak to the old generation of fridgies, the guys who are now thoroughly retired, they all tell you long stories about working with methyl chloride and sulfur dioxide, and a lot of fridgies did get killed back then. So it was nasty stuff. And because of that, the so-called safety refrigerants were developed, the CFCs, the HCFCs, and unfortunately with them, many of the problems that we have today. So this gives you a bit of an overview of the refrigerants that are still, or that ever were, in use. So we have, as I said before, two categories: the synthetic refrigerants and the natural refrigerants. So synthetics are substances that do not exist in nature, which is an important point because it means that there's no mechanism to digest them when they escape. And that's part of the reason why they have environmental downsides, because when they are released to the environment, they linger, sometimes for hundreds of years. And if you look at the table, all the substances with marked red have been phased out or are being phased out for those reasons. Refrigerants have two measures of damage to the environment. The one is the ozone depleting potential, or ODP. That was recognised back in the 80s, and the badly ozone depleting gases were banned in 1989 already. And that's, you remember the slip, slop, slap, or you might even be too young to remember the slip, slop, slap, but that was done to protect us from the damage in the ozone layer, which is slowly busy mending now that we've done this. So the CFCs and the HCFCs, they were banned back in 1989. And just recently, the HFCs, which are the follow-up refrigerants after that, are also being banned. And the reason for them being banned is because they have a high global warming potential. And at this point, I tend to give you an idea of the magnitude of that. R404A is a very good example. It's a gas that's still commonly used in supermarkets. 1 kilogram of 404A, if it was a liquid, would fit into a large drink glass. 1 kilogram of 404A is equivalent to 4 tons of CO2 in its global warming potential. Now, what is 4 tons of CO2? 4 tons of CO2 is what your car, a big 6-cylinder car, would emit if you drive it for 25,000 kilometres. So that is a large amount of fuel that you have to consume in your car to generate the same as 1 kilogram of that gas. And a supermarket might have a ton of it in there. And 20% of it might leak every year. So that's why the impact of refrigeration up to now on climate change has been disproportionately large. Refrigeration and air conditioning have an impact greater than all of transport for that reason alone. And that's the reason why these gases are being phased out. So all of those are now marked red, and I'll explain in the next slide why. And the only synthetic refrigerant still left, or that's still being, well, it's actually just come onto the market, is a category called the HFOs. They're flammable. And then the category below that, which I've marked green, are the naturals. So ammonia, and I can say ammonia, every one of you generates 18 grams of ammonia every day, whether you like it or not. So ammonia is natural. Carbon dioxide, you exhale carbon dioxide all day. And then hydrocarbons, we use it in our barbecue every day. Well, if we were to barbecue every day. So which refrigerant are you using? I get interesting responses to that. But typically this will be the answer. So most likely you'll be using gases like R134A, 407F, 507 and 404A, and all of these are HFCs, and all of these are about to be phased down or phased out. Or you could still be using R22, which is an HCFC, and that's already been phased out. So if you've got R22, you better get rid of it fairly quickly, or you may not get it. And then there are a category of blended refrigerants that have come onto the market as intermediate stopgap solutions. So you might have 448A, which will see you through for a number of years. However, if you're lucky, your system might be on either carbon dioxide or something like R290, which is propane, or ammonia. Now, why is all of this so important is because of what you see on the slide now, which is the phase down of refrigerants. As of 1st of January of this year, of 2018, all HFCs have commenced a phase down. And it's the amount of gas that is imported into the country. We don't manufacture refrigerants in this country, so it's quite easy for our government to control it. Just what comes in, we can regulate. So there's now a quota, and it's based on the 2014 imports, and right now we've gone 25% down. Now I know that the wholesalers have obviously stockpiled a lot of gas, so right now there's not a shortage yet, but the shortage will come. Because we're a growing population, we need more and more refrigeration and air conditioning, we're going to be using more refrigeration, not less. But the gases that we import are going down, not up. So inevitably, if we don't do anything differently to the way we've done it up to now, there's going to be a shortage of refrigerants. 2 years ago, in Europe, they started the same process. We're 2 years behind the Europeans. And this year, Spain ran out of R404A. A whole refrigerant was not available in a country. Italy ran out of 410A. And there was a massive shortage of 404A in the UK. And a lot of the fridges are Brexit proponents because the intention is to renege on those phase-outs once Britain exits the EU. So unfortunately, that's one of those things which is happening. So all these phase-outs are a positive thing or a good thing. They should have happened 20 years ago, but they are happening. So we are seeing the industry being forced to use less of these damaging gases. From an energy efficiency perspective, this is an opportunity, because the energy efficiency of the new gases, or the systems that you can build with the new gases, can be very high. But being compelled to replace your systems because of a phase-out gives you the opportunity to put in better systems. And that's what we're trying to do. And why do we have to look at these? It's because refrigeration systems leak. There's nothing we can do about that. Copper is unfortunately the widest used material, and copper has the material property that it hardens all by itself. So if you take a piece of copper when it's brand new, it's nice and soft, and you put it up on the shelf, and you can take it off 10 years later, it's a lot harder. All by itself, it just hardens. It's a crystallizing process. And if you subject that to temperature change and vibration, that process is accelerated. So if you install a refrigeration system today, after a couple of years, the copper starts hardening, and then it starts cracking, and then it starts leaking, and there's nothing you can do about that. So yes, you can build things better and prevent vibrations and blah, 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 and that is being done. But ultimately, it's impossible to build a refrigeration system that does not leak. So they will leak, and this table shows examples of the leakage rates per annum, and they are still pretty high. So we need to get over that as a society. So unfortunately, there are no magic solutions. So there's no immediate gas that I can just take the bad stuff out and put the good stuff in. It's not that simple, unfortunately. We've exhausted all replacement opportunities. So there's no easy replacement. So effectively in the future, we need to look at things like ammonia for the large applications still, carbon dioxide increasingly across the range from very small even to pretty large, hydrocarbons for the smaller systems, and that change has largely already happened. If you go to a Harvey Norman or any of the other retailers and you buy a fridge today, the chances are 99% that that fridge will be on a hydrocarbon refrigerant. 10 years ago, that was not the case. So the commercial or the domestic refrigeration industry has already made that transition. The commercial industry still has to make that transition. So all the other gases that we are familiar with, and literally all, are not future-proof. In 15, 20 years' time, they'll all be gone. My son is a refrigeration tech, and when he started his trade, I told him, son, when you're my age, you'll only be working with flammable refrigerants and toxic refrigerants and refrigerants that are both flammable and toxic. And that's all that'll be left. And unfortunately, that puts a great constraint or a great pressure on our industry to do the right thing, be safe, get training, and we have a big deficit in our industry in terms of training, and I see that as being one of the challenges in rolling out the new technologies. Carbon dioxide systems are increasingly being used to displace even industrial systems. I've seen just recently examples of major ammonia systems instead being built with carbon dioxide. But certainly they're available across the range. Most supermarkets are now considering or putting in carbon dioxide systems instead. And there are a range of different solutions even within carbon dioxide that I have on the screen at the moment. The full carbon dioxide system is the one that is currently seen as the solution. So why carbon dioxide? Well, first of all, it's safe, although carbon dioxide can asphyxiate you. If you were to fill this room with 10% of CO2, you will not be very happy. But your body reacts to that. You feel threatened by it. It's easy to detect CO2 in the air and make your way out. It's effectively, therefore, non-toxic. It certainly is not flammable. It gives you very low running costs, which is, of course, interesting. That's why the retailers are doing this. So you can save electricity and fuel. And the reason why you can save fuel, I'll talk about that later, because it's very good at generating hot water at the same time. It's certainly future-proof. Nobody's going to phase out carbon dioxide. In fact, it's a way of storing it and keeping it out of the atmosphere by putting it in a refrigeration system. But we use such minuscule amounts, it doesn't really make a difference. But there'll be no phase-downs, no phase-outs, no taxes, no levies on carbon dioxide ever. So currently it's reached the point where if you if you install a CO2 system and you use it to generate hot water, it actually becomes the cheapest solution that's available. So there are very few hurdles to its wider use, except knowledge and training. And we talk about the thing called transcritical CO2, and that terrifies many people. What does transcritical mean? I won't explain it in great detail, but it's just a thermodynamic term. Every substance, there's a certain temperature above which it cannot turn into a liquid. And on carbon dioxide, that happens to be 31 degrees. It doesn't mean you can't use carbon dioxide above 31 degrees. We just have to design the refrigeration system because there's going to be no liquid. It's just a gas. So from an engineering perspective, no problem. In fact, the fact that carbon dioxide systems run transcritical gives us the big advantage of the hot water, which I'll explain in the next system, or next slide, in fact. So carbon dioxide systems can generate a large amount of hot water very easily. Why is hot water useful? Well, hot water is for domestic hot water. If you have a food processing system, you want hot water to sterilize things. You need hot water to heat things. So if you had a refrigeration system somewhere and you've got a cold building next to it, you could use hot water to circulate that for heating. So fascinating thing with carbon dioxide is that you can actually recover all of the heat as useful heat. With any other refrigeration system, it's maybe 5 or 10% or less that can be recovered at a useful temperature level. I'm not talking 30 degrees, I'm talking 50, 60, 70 degrees. On a CO2 system, you can recover 100%, either as 60 degrees wash water or as 90 degrees sterilizer water. So in the dairy industry, for example, this is really creating waves because you can now have a refrigeration system that generates all the hot water you need for all the cleaning processes in the dairy. So it becomes kind of the ultimate solution. So it's a good thing we have that, and it's kind of ironic that carbon dioxide, which has been so maligned because of its global warming potential, is being used as a refrigerant. But remember, it's got a global warming potential of 1, because that's the datum of GWP is carbon dioxide. So why would you improve your refrigeration systems? What motivates you to improve your refrigeration systems? Essentially 3 things. You want to reduce your running or your maintenance costs. Now that's if your system is old and it's leaking gas and it's leaking oil, that's a constant maintenance cost. And especially with the phase downs, refrigerant costs will spiral, and you will have greatly increased maintenance costs in future with the synthetic refrigerants. Good motivator to move away from them. Then you want to future-proof yourself against the gas phase-out. So if you're using R22 gas or one of the HFCs, there is a risk. There's a business risk that one day you may not be able to get the gas and you lose your refrigeration, or you just can't afford to pay for the replacement gas. That has happened in the past. And then finally, you want more reliability. You want a system that keeps running. You don't want to be awake at night wondering whether your refrigeration system is running. So these are the 3 motivators why that would encourage you to improve your refrigeration system. And then the second question is, do I replace my system or do I retrofit it? The instinct is to retrofit it. I've got this gas. What other gas can I put in there and keep running with investing as little money as possible? That may in some cases be the right solution. In many cases it's not. There are many systems out there that have already been retrofitted once. So remember we had the CFC phase out and then they retrofitted that onto an HFC. Now you're definitely not going to retrofit it a second time. So my advice is if it's already been retrofitted once, don't do that again. It's well over its use-by date in any case. If it's at the end of the life, and commercial refrigeration systems generally are at end of life after about 10, 15 years. At the coast it's more like 10. But there are systems out there that are 25 years old and they're certainly over their use-by date. So don't spend your money on retrofitting those. And if it's degraded, and I'll show you pictures later of what a degraded system can look like, don't spend your money on a degraded system. You can't fix it, you've got to replace it. And then finally, I see this very often, if the site needs expansion or the site uses have changed, you have a site that did one thing in terms of its cooling and heating a few years ago, the needs have changed, the processes have changed, the supermarket arrangement has changed, so the systems no longer quite match what you had 5, 10, 15 years ago. And that makes the system inefficient. having an undersized or oversized system. I'll show you when we do this, talk about the study results of what undersizing and oversizing can do to it. Stop, replace. However, you could have a system that's 2 years old and that is otherwise running fine. That is, you've just invested a lot of money into it, the equipment is still sound. There is an argument to be made to retrofit those. There are some transitionary refrigerants available, like R448A, which could get you across the next 10, maybe 15 years, if you're lucky. Or if you just need a short-term plan. If you have a system which is on R22 and you just need to get over the next 3 years before you move to new premises, well, there's potentially a solution for that. Or thirdly, the solution, which isn't really, or the option, which isn't really a very good excuse, is if you don't have capital. If that is the only reason why you're not doing this project, there are ways to finance a project with energy efficiency finance, and you can talk to Sustainability Victoria to advise you on options there. So, buying cheap can be expensive. This is an old idiom, old axiom. If you pay little for your system, you quite likely will have a system that uses more energy and costs more to run. It'll probably require more maintenance and hence more running costs. It'll probably have a shorter life. And when I talk about the condensing units and the condensers later, you'll see what I mean. So that'll increases your annual cost of ownership. And if you've bought something cheap because it's being phased out now and people are trying to clear their stores, you could end up with something that'll be phased out pretty quickly. Unfortunately, we see a lot of that still happening today. Thank you. Sustainability Victoria supports action on climate change and reducing energy costs. If you would like to find out more, please visit the Sustainability Victoria website.